Okay, so why industrial ventilation? In industrial hygiene, we prioritize the ways that we protect workers. Okay. We start off with protecting a worker by using engineering controls. What's an engineering control? Engineering control is you physically make the job safer. You make some engineering change or choice, makes the job safer. That could be machines that use double switches. You've seen a lot of these probably films where a guy is using an embossing plate or he has a stamp of some kind, and the machine will not drop the embossing machine or the stamp, which is heavy and is a finger eater. It won't drop it unless he presses both switches at the same time, and he needs to have both hands away from the equipment in order to press both of those at the same time. You have guards on machines. Those are engineering protections, right? They keep a hand from going into those. You got your table saw at home has protection from the blade by having a guard over the top of it that lifts and follows the wood and above the wood and stays in place, so you're not exposed to the direct blade. I have a friend of mine just spent a lot of money. He's a really good carpenter, amateur carpenter. He spent a lot of money, believe it or not, on a table saw that senses when it comes in contact with living material. And it literally will stop if you put your finger in it. He tried it with a hot dog and it worked. There was a little mark on the hot dog, but it did stop. Let me see if I can't find a picture. I see some of you guys don't really believe me. Yeah. Hang on a second. He didn't use his finger, that's for sure. Table saw. Finger. Sensing. Oh, so you have access to one of these? Okay. Yeah. It must be capacitive or something like that. It must be electronic. There must be the blade must sense that it's a certain kind of, like the conductivity of the material or the capacity. There you go. It stopped right when he. Wait, hang on a second. Yeah. I don't think you're gonna find somebody use his finger. Let's see if this guy. I hope this. I just saw this one. I hope it's one where like he doesn't get his finger cut off. Okay. Oh, wait a second. Yeah, he put his finger in it. Got a little scratch on his finger. Now notice he did it very carefully. He literally moved his finger up to it. He just touched it. Boom. Cool, right? That's amazing. That's an engineering control. Somebody invented this. Imagine that, right? Now all they got to do is cure the problem of the kickback, and they'll really be safe, because that's even more. You ask me, that's even more dangerous than hacking a finger off. That can make a piece of wood fly back and kill you, for instance. I won't get into that because you guys that use table saws know what kickback is. Okay, so that's an engineering control. Sometimes you can't completely protect the worker. You can't remove the removing a chemical hazard, substituting a less dangerous material for a chemical, right? That's an engineering control. So you physically remove the hazard. The hazard's gone. It can't hurt the worker. A lot of times you can't do that. The exposure hazard part of the job. A toll worker is going to be exposed to carbon monoxide. Other people, nail salon worker is going to be exposed to acetone. By the way, I use acetone a lot as an example of a chemical hazard, VOC, in a work environment for nail salons. There's a lot of other stuff that's in fingernail polish that isn't particularly good for you as well. We'll talk about that another time, right? So an engineering control there might be a hood, a ventilation system to pull the fume away from them. Sometimes that's not manageable, or it's only partially protection. What do you do then? Then you go to administrative controls. At the toll booths, for instance, you can only work for some, a radiation, or if you're exposed to radiation, you can only work in that environment for a certain period of time. They monitor your exposure. When you get to a certain level, you can't work there anymore. You got to work in this other area of the plant for a while. That's an administrative control. The work rules are: you don't do this, and you don't go repair this machine unless you lock out the machine so it can't be powered. Right? That's lockout, tag out. That's an OSHA standard. That's an administrative control. It relies on them to follow the rules, right? It works pretty good, but they got to follow the rules, right? And then finally, if neither of those provides complete protection, that you're still exposed to a fume or noise, for instance, you still have an exposure to that, you protect the worker using protective equipment. So personal protective equipment is the last line of defense. If you've gotten to personal protective equipment as your defense against a hazard, in a sense, as an industrial hygienist, you failed. You haven't engineered the danger out. You haven't managed the danger out. Now you had to go to personal protective equipment in order to keep the worker from being exposed, right? So it's kind of a little bit of a failure. We're going to get into personal protective equipment later on, because all of this is part of having to deal with a hazardous environment. As far as VOCs, particulates, anything that you would breathe in, this is a great engineering control. That actually is not a great engineering control. That's my basement fan, right? But you get my idea. Ventilation is a good way of capturing a hazard that might get into the air before the worker has a chance to be exposed to it. A lot of different kinds of ventilation. One form of ventilation is industrial ventilation or capture ventilation. What you do is you take a fan in the work area, you have the guy work so that the fan is sucking air in the vicinity of where he's working. And it's pulling the air in fast enough that as he generates the hazard, if he's doing welding, for instance, or if he's soldering, as the fumes are being generated, they're all being captured by this device, by this hood, right? And you only need a little bit of air, because if he's working in a small area, a fan like this might be sufficient to provide the capture that he needs, especially if he's got a hood that's designed properly. Capture the fume so it doesn't get into the air, he doesn't get an opportunity to breathe it. On the other hand, there's other kinds of ventilation that they use industrially as well. Dilution ventilation. We're standing in a room right now where we're controlling odors using dilution ventilation. Air's coming in through these diffusers, right, into this room. The air is conditioned air, it's coming in, the right temperature, it goes into this room. And then after it leaves this room, it goes through, there's probably a slot at the back or something like that, where the air gets pushed up into the ceiling, and then it gets sucked all the way back to the air conditioning equipment again and gets recirculated continuously. In and out continuously. We might get in this room, typically you can see there's a diffuser in the back corner over there that goes up into the ceiling. Air's coming in through there, and it's probably going back up into those two diffusers in the ceiling they see that are in the place of these these ceiling tiles, right? So if we just recirculated the air all the time, it'd get pretty stinky in here pretty quick, right? Whatever odors we generate would hang around here. They'd build up, accumulate. So what they do is a certain percentage of this recirculated air is dumped outside and replaced with outside air, fresh air, right? That's called dilution ventilation. In order to control a hazard using dilution ventilation, you need a hell of a lot bigger fan than this. You have to change massive amounts of air in order to make that effective. Not only that, but even if you do that, the contaminant is still in the air. You're just reducing the level. So you're still exposed to the hazard. So dilution ventilation is not as good as exhaust or capture ventilation. It also wastes a lot of energy. This is moving probably a couple of hundred cubic feet per minute. The device that's dumping air and picking it up is moving thousands or tens of thousands of cubic feet per minute of air. That air has to be heated again in the wintertime, has to be cooled again in the summertime. So it costs an enormous amount of energy.
Sometimes it's not a concentrated level of most dangerous. Perhaps it could be a level.
Yeah. Yeah, sometimes you're not, because it's below threshold, you don't smell it, you don't know you're exposed to it, and so on and so forth. Okay, let's talk about air. Air is 78% nitrogen, right? Gives you an idea of what the molecular weight of it is. It's very close to the molecular weight of nitrogen. So you can use that kind of use that to kind of make a judgment as to whether something's going to rise or fall, right? Going to tend to go down or go up when you release it into a room with air in it. Why is that important? Because you can use that to your advantage. In other words, if you're in a restaurant, you have a giant stove in a restaurant, a giant cooking area in a restaurant, you're going to put the hood over the top of it because the warm air is going to tend to rise. If you have a material that's going to tend to that's heavier than air, you're going to design your hood or your mechanism to take advantage of that. So a good industrial hygienist, and I'm not turning you guys into industrial hygienists, he's aware of these characteristics of air. Standard temperature, pressure, dilution. Okay, good. Okay, where do you use? So local exhaust ventilation is usually used in situations where you have a bigger hazard. A lot of times you'll get away with dilution ventilation because the hazard is relatively low. But if you have something that's a real hazard, then you want to make sure that you capture it as efficiently as possible. You don't want the worker exposed to it at all. Toxic substance, high production operation, chemicals with strong odors or irritating, flammable liquids like spray painting. They have spray booths where they do spray painting, and so on and so forth. Um, uh, some work operations where they use it, grinding. You guys have noticed that maybe 10 years ago, when they would repoint buildings. Repointing is the process where they take the grout between the bricks and they grind it out because it's getting brittle, right? Nasty and brittle. They grind it out and they replace it with fresh cement or mortar between the bricks, right? So the problem with that was that they would do it with no protections at all. Just put up scaffolding, start grinding. If you walk by on the street, you get covered with the silica and the dust from it and so on and so forth. The workers had enormous exposures because they used grinding equipment. Nowadays, when you see them working with that, they're using grinders that have hoods on them. They're connected to vacuum systems. Greatly reduces the amount of particulate matter that gets into the air because it's under a great suction, it gets sucked in as it's grinding, those grinding materials get sucked in. If you're an amateur carpenter, most at least medium level equipment for amateur carpenters nowadays has connections on it for you to put vacuum hoses onto so that you can control the amount of wood dust that you produce. Not just to keep it clean, but hardwood dust, for instance, is a known agent for nasopharyngeal cancer. So you want to reduce your exposure to wood dust as much as you can. So any kind of thing that's a real hazard, you want local exhaust ventilation works very well. Of course, the classic local exhaust ventilation is a laboratory hood. Yeah. Well, just what you're doing. Oh, the occupants inside. It's not so much them. It's the people on the street or the building across the street that might have their windows open, or the occupants if they have their windows open. Most of the stuff you're generating, if the windows are reasonably well sealed, they're not going to get into the building. But if you have windows open, then definitely it's getting into the building. And in fact, I've been in situations where they've asked me to come in and do, a tenant asked me to do wipe samples because they were getting dust from the neighboring building and stuff like that. It hadn't occurred to them to close the window, but that's a whole other thing, right? So, yes. Oh, yeah. Yeah. Well, yeah. If it's getting into the building, yeah. If it's not getting into the building, no. Right. And we have equipment. We have particulate monitors that you can measure what the particulate levels are inside the building and see if while they're working, if you're getting spikes on it, if they're really contributing to it. Yes. Yeah. Yeah. Well, I guess also if you keep it under most facilities, like a room like this, are under a positive pressure. Of course, we're pushing air into this space. Ceiling's under a negative pressure, but this room's under positive pressure. Positive pressures tend to leak out rather than leak in. But you open a window up and now you kill that positive pressure, right? So air can move in and out. And if the windows are leaky and so on and so forth, like I said, the people on the street, neighboring buildings and so on and so forth, they're much better at this now than they used to be, because they use water or wetting agents to spray the materials so you don't get as much dust. They should be using hooded grinders and capture ventilation systems. That's what this is all about. Capture that particulate before it gets to the building, before it gets to the street, and especially before it gets into the lungs of that worker that's grinding that stuff. That stuff's really dangerous. It's a cement mortar or cement. A mortar is a combination of cement and some other media like sand or silica or something like that, right? So when they grind that stuff up, they get silica particles, crystalline silica particles. They breathe that stuff in. It can be very damaging to your lungs. The mortar itself is alkaline, so it's very irritating and bad for your lungs as well. So it used to be they would work with almost no protections at all. Now you see them wearing respirators. You see them using these hooded grinders, right, as opposed to just an open face grinder. And if they use it properly, it can go a long way to cutting down their exposure. From my perspective, my first concern will be the worker, because he's the one that's got the exposure. Everybody else got a small exposure. That guy's got a much bigger exposure than everybody else does. Okay, so there's a couple of things that were interesting that you should bring this particular thing up, because one of the things when we design these kinds of things, one of the things that we have to keep in mind is that we have to be cognizant of what velocity of air that we need when we create a vacuum system, that we need to capture this stuff efficiently and to keep it moving once it's in the ductwork, once it's in our ventilation system. Capture velocity is the speed that the air has to be going at in order to capture the material and take it out of the worker's breathing area, right? So if I'm soldering a circuit board and I'm getting these light fumes, fumes are the fumes could be VOCs from the fluxes that they use, but they could also be some tiny metal particles depending on what temperature that they're soldering or welding at, right? So those are very tiny. VOCs and very tiny particles act like gases, and they're relatively easy to capture because you just have to make sure you have enough velocity to pull them into the exhaust system, into the hood. Grinders, on the other hand, big particles may be coming off of that, right? Chunks and pieces and bits and so on and so forth. Those are bigger particles. You need a much higher velocity to capture those particles and to pull them into the hood. That's part of the basic nature of designing these systems. We're not going to teach you how to design these systems necessarily, but I'll bet you between this week and next week, you're going to be in a pretty good shape to be able to tell when they're not working right. Okay? Transport velocity. Now that you suck this stuff into the ductwork, you got to get it through the ductwork, out of the building, and somewhere where it's safe, right? You might have to filter it out and so on and so forth. You need to have enough velocity of air moving through the ductwork so that the stuff doesn't drop out and clog up the equipment and eventually wind up clogging up your ductwork and stuff like that. Yes? When they drop stuff in the ocean? How do you mean? Oh, you mean, that's a good question. I wouldn't necessarily, when I say capture velocity, I'm talking about like how much air you have to be sucking in order to grab the contaminant, right? And when I talk about transport velocity, it's more about what you got to do to keep it moving through your equipment. So they're all the ships. Who knows what they do out in the, when they're really out there, who knows what they do at waste and the smokestacks and everything else. Ventilation system measurements. Okay, so we're going to talk about how to measure these systems and judge whether or not they're doing what they're supposed to be doing and how much air is really going through them, because that gets a little complicated measuring these things. Okay, so one of the ways that we're going to look at this, let me see if I can't find that picture first. I don't want to talk about that yet. Okay, so let's take a look at air moving through a duct, because almost all ventilation systems are going to wind up consisting of a hood, a thing where you're going to capture the material. I got one over here somewhere, like this. This could be a hood, a lab hood with the glass that comes up and down. That's a hood. Anything can be anything that's the point at which you're doing the capture could be considered a hood, right? So it's considered consists of a hood, typically an air cleaner, because usually if something you don't want to expose the worker to, it's something you don't want to expose anybody else to, so you got to take it out of the air. If it's particulates like grinding material, then it's probably going to be a media filter. If it's VOCs, it may be an activated charcoal filter. But you want some way to scrub it out of the air. Then the fan, notice the air cleaner is in front of the fan. Why not? You might as well protect the fan too, right? And then an exhaust stack to get it out of the area that you get to move the air that you're moving completely out of the building. So this hood, all of this stuff is connected with some transport mechanism, ductwork, right? So you need to understand how this air is moving through this ductwork so that you can really actually design this system. Okay, so now air doesn't move linearly through a duct system. At the velocity that there's something called turbulent flow and laminar flow. Laminar flow is when fluids are moving very slowly and they're all moving, or the whole thing is moving at the same rate. Not eddy currents, not anything else is moving straight through. That's not what's happening in here. This is moving very quickly. There's friction on the outer edge where the air is hitting the outer edge. So what winds up happening is that the flow through here is turbulent and it's uneven. In the middle of the ductwork, the air is moving faster than it is on the outside of the ductwork. So it kind of looks like this bullet-shaped curve here that's showing the rate that the air is moving through here. It's showing it as something called velocity pressure right now, but that's really the way that the air would be moving through here. Okay, so we have to be cognizant of that because that affects how we measure the amount of air moving through here. An example here, here's a hood. Also, in order to calculate what the velocity, how much air we're actually moving, we have to keep in mind that there's a couple of basic equations here. The first equation is the quantity of air that you're moving is equal to the velocity times the area in square feet or meters of the area of the ductwork that it's going through or the hood that it's going past. Okay, what does that mean? For instance, in a lab hood, if the lab hood is 12 inches up and 24 inches wide, okay, if the opening is 12 by 24 inches, what volume of air is being drawn through that hood? If the average face velocity, the velocity of the air moving through it is 200 feet per minute. Well, you have 2 feet by 2 feet, 12 inches by 24 inches, times 200 feet per minute. So there's 400 cubic feet per minute being pulled through there if the face velocity is 200 feet per minute. If the velocity going past the front of this is 200 feet per minute and it's 1 foot by 2 foot, that means that you have 400 cubic feet per minute going in here. What if I told you that you had 800 cubic feet per minute being pulled through here? What would that do to face velocity? It would double the face velocity also, right? If this is 800 and this still is 2 square feet, then this would be 400 feet per minute face velocity. It's pulling air in quicker. If you have a hood that you're working with that has a relatively non-hazardous material you're working with, you might want to keep it a face velocity air getting pulled in at 50 to 100 feet per minute. If it's a more dangerous material, you might want to keep it at 200 feet per minute to ensure that whatever's in that hood stays in that hood. Okay, so there's our basic exhaust system. You got ductwork, you got a hood, you got an air cleaner, you got a fan, and you got a smokestack. Here you got the hood. This represents the hood. You got the ductwork, you got the fan, and you got an exhaust system. But you don't have an air filter on this particular one. But this is a rudimentary hood. You can actually use this as a hood. Yes.
I'm sorry. When you mentioned scrubbing before, is that what the air cleaner
Yeah. Sometimes they call it a scrubber. Yeah. Sometimes they call it an air cleaner, a scrubber, a filter, and so on and so forth. Okay. So ventilation system components. This is an axial fan blade. You have many other different kinds of systems. You have this is a paint spray booth. It's just a booth that you're pulling air through. They're just using aerosol cans there. You can have systems on ductwork where you have elbows, where you have transitions, you have and so on and so forth. That once you start to design these systems or look at these systems, they can get pretty complicated in terms of the transmission equipment. But the basics are always going to be this idea of a hood, transmission system, ductwork, an air cleaner, and a fan. Okay, always going to have a certain amount of that that's going on. So how do you know how well this is working? Well, one way is to visualize it, to actually use smoke tubes or simple mechanisms like that in order to be able to tell how fast the air is moving into the hood, and if you're really capturing the material that's in there. That's qualitative. It's not quantitative. You don't know for sure. You're not really measuring it, but you have a pretty good idea of whether something is getting pulled into the hood or whether it's not being pulled into the hood. You have instrumentation, and we have a few of these here that we're going to be playing around with at some point. Maybe not today, but we will get to it at some point. One of them, any instrument that measures the velocity of air is called an anemometer. Right? You have digital anemometers, right? They have digital readout. You have analog anemometers such as this, and you have different mechanisms for these things to work. This one uses a axial fan blade. I think I got one of these here. It's sometimes called, do I have it out there? I know I have it. Let's see. There it is. This is called a vane anemometer. Right now it's set on units of feet per minute. In the United States, everything we do in ventilation is usually in feet, cubic feet, and minutes in terms of volume and in terms of pressures. In most ventilation systems, you're talking about, instead of PSI or other pressure measurements, usually talking about inches of water. Imagine this, instead of talking about a pressure in terms of pounds per square inch, you talk about a pressure in terms of this pressure, how many inches of water will it hold up in a column, right? That's why we call it inches of water. One of you guys want to come up here and do me a favor? Somebody come up. Somebody, I need another hand. Oh. There you go. Hold that about a foot in front of that. Okay, get a little closer. Get a little closer. Turn it around. Up, there you go. Oh no, you got to hold it perpendicular. Flow there. Yeah, as best you can. Okay, so right now you're reading about 175 feet per minute. That's the velocity of air that's moving through that point. Move out and double that distance. Up, stop there. Hold on a second. It's not even going fast enough to spin the blade. Okay. One of the interesting things you're going to find about exhaust ventilation is that if he got only about a foot away from this duct, you almost can't feel any suction at all, right? Why is that happening? Because air is being pulled in from all directions here, right? So it's very inefficient. How can you make it more efficient? By designing a hood around it, such as this. So you kind of enclose the area that you're going to be working in, and so that you can pull the air in efficiently without pulling stuff around it. You can put a flange out alongside of this that covers the outside that keeps air from wrapping around and going inside of it. So a lot of techniques you can use to make these hoods more efficient, and you'll be able to tell if I turn this around, you feel the same amount of air is coming out of there is coming out of here. You'd feel this to the back of the room. on the discharge side, right? Ironically, the side you need is the one that is harder to design to work efficiently, right? But that's the side we need. We don't care about this because this is the part of it that we're just exhausting air from, right? So one of the ways we can measure this is with a device called a vein anemometer. Another type of device is called a thermal anemometer. This has a little heating element in it, and it measures the velocity by telling how much heat is being pulled off of this little heated resistor at the end of it. So let's give somebody else come up and give this a try. Yeah, hold it about 6 inches away. Yeah, you read it. Okay, you're about 3 inches away. Yeah, that's okay. Get this right in the middle. There you go. Yeah, that part. That's what's reading. There you go. Yeah, what are you reading?
262. Well, now it's 249.
Oh, yeah, don't worry. It's going to jump around. It's about 250 feet per minute. She's a little closer. Double that distance. That's not so far. But yeah, okay. What do you got in that map?
54.
54.
Well, now it's going to 80, 73.
Right.
75.
So it's diminishing very quickly as you go further away. Okay. So that is part of what we're concerned about here. So in other words, one of the things that we do when we design this, we're concerned about capture ventilation. If we need 250 feet per minute capture ventilation, that velocity air to capture it, the guy better be working 3 inches away from this hood. Because if he's working back here, he's not getting the velocity he needs to capture the contaminant. If he only needs 50, he can work as far back as here, right? But that's part of the design of these things. Okay, and this is a thermal anemometer. The nice thing about these things is you can really stretch them out, and you don't have to be, when you use the vein anemometer, you kind of get your hand in the stream, and it's kind of like makes it a little bit less accurate. With this, you can at least be out of the stream of air. So these are a little bit more efficient for testing hoods. We're going to talk about in a second how we actually measure hoods.
You have to be tested right there in the strip.
I'm sorry?
You have to like have it close to the strip of the thing.
I'm not sure I understand.
Oh, because I think you were saying for her to move a little bit closer.
Oh, only because I wanted to get it some measurement.
Oh.
Okay, at the point, yeah, she was 3 inches away, right? She measured 250. The minute she went to 6 inches away, it dropped down to 50. So there's an enormous amount, the impact of like distance on this is enormous. And the way we get around that is by building the hood so that it doesn't pull air in from places you really don't need it. It directs the area that you're going to pull air in from. So in this case, here's some more instrumentation that you might see. This device up here, the blue thing, is called a bolometer. It measures, it's not an anemometer. It doesn't measure air velocity. It measures air flow, quantity of air that's flowing in cubic feet per minute. This one is designed this way with those two handles so you could hold it up over diffusers in the ceiling and actually measure how much is coming out of each diffuser when you're testing air. This guy that's next to it there, he's using a thermal anemometer that's being held inside the ductwork to measure the velocity that's inside the ductwork. We're going to talk about that in a little while as well. Okay, and then there's some other kind of device. This device that you see here is called a manometer. Okay, and it uses a liquid, water typically, in order to measure pressure rather than velocity. Once you can measure pressure, then you can use the pressures to determine what the velocity is that you're dealing with. Okay, we're going to look at some formulas that are involved there in just a little bit. Okay, I want to see where we are, where time flies. Jeez. Okay, so now, next week we're going to talk about pitot tubes. Anybody knows where you might see pitot tubes? You've seen pitot tubes, right? Right? Anybody here flown in an airplane? Okay. Right, you've all flown in airplanes. Okay, the way a pitot tube works is we got 5 minutes. Just give me 5 minutes. I know you're getting restless. I can hear it. Okay, the way a pitot tube works is in ductwork. I want to get a good picture. I don't like that one. I like that one. Okay. I have a Pitot tube here somewhere, right? Pitot tube. You see it? Yeah, it goes with that thing, but it's not that thing. Hang on a second. Here's a big one. Here's a big one. It's easier to see. This is a Pitot tube, right? When I turn this thing on, I'm not going to turn it on and make noise. When I turn this thing on, air is going to start moving through here. It's moving through here because this fan is producing a suction, right? If I turn the fan on and I cover this entrance to this ductwork, there's still a negative pressure in here, right? It wants to suck air in. And as you can imagine, if you've ever put your hands over a vacuum cleaner hose, right, it can suck pretty hard, right? When you have your hand over it, that suction is potential energy. That suction is energy that can be turned into, when you take your hand away, the moving air. That's kinetic energy. When something's moving, that's kinetic energy. When something has the potential to make something move, that's kinetic energy. So that pressure that you feel in there, if you cover the end of that hose, that pressure that you feel is static pressure. That the no air moving, is standing still. That's the pressure that's in that hose or that ductwork when the air's standing still. And so it's called static pressure. That static pressure will determine how much air you can pull through there, how much velocity air you can pull through there. Okay, static pressure is the same in all directions. Okay, once you cover that, air's not moving. The static pressure acts the same way in every direction. It's a negative pressure because it's sucking. And if you put a hole in here, a hole on the bottom, it would pull air in, because it doesn't matter what part of the ductwork you're on. Static pressure is always same direction. Velocity pressure is the pressure that you feel when air is moving and it hits you. For instance, the wind, right? If you stand out in the wind, you feel pressure from the air moving and hitting you. That's called velocity pressure. Here, when you're standing here, the static pressure is 14.7 psi, right? The static pressure is the air pressing on our body from all directions. That always changes, it's always pushing against us. Velocity pressure is when the air is moving and hitting us, and we can feel that pressure from that air hitting us. That's velocity pressure. You add the two of them together, and you get something called total pressure. It's the sum of the velocity pressure, which is the static pressure, which is acting everywhere, and the velocity pressure, the pressure from the air pushing against you. This thing measures both static pressure and velocity pressure. And the way is from the movement, right? It's a directional. Static pressure is omnidirectional. The way that this works is that as air, if I put this in here and turn it, it's going to be facing this direction, right? And we can connect the tube here and measure the pressure of air moving through this ductwork when the fan's on and going into this end of this tube, right? Is that total pressure or velocity pressure or static pressure? Which is that? What is that measuring when the air's hitting here? Velocity and static. It's both, right? Because the static pressure is acting everywhere. This is total pressure, not velocity pressure, total pressure, right? So this is total pressure and velocity pressure. In this tube, there's really two tubes in here, one tube and another. There's little tiny holes around the edge here. And those little tiny holes are connected to the other part. I'm not sure which ones. I think that one is the outside, one's the inside. Those little tiny holes are on the side. So the air is moving this way. It's not feeling the velocity pressure. What's that measuring?
Static.
That's static pressure, exactly. So I have total pressure, and this is measuring static pressure. So one's measuring total pressure, one's measuring static pressure. If I take static pressure and subtract, if I take total pressure and subtract the static pressure, what am I left with? The velocity pressure. The velocity pressure tells you how fast the air is moving. So this device, by measuring the difference in the static pressure and the total pressure and the velocity pressure, this device will tell you how fast the air is moving. Where might that be important? Bingo, right? Doesn't matter what the ground speed is. Your airplane could be going 400 miles an hour, right, or 500 miles an hour. But if the airspeed is not high enough, the velocity in the air is not high enough to keep it in the air, then you have a problem. And let me just show you a couple of pictures, and then you can run out. I still have 2 minutes. Don't get so restless. Here are Pitot tubes. Here's a Pitot tube on an airplane. Every airplane you'll ever be in uses a Pitot tube to tell what its air velocity is. Without that little device, which isn't much complicated than this, with a little heater in it, keep it from freezing up, you will not be able to keep that. You will not know how fast that plane is moving through the air. A Air France plane crashed about 5 years ago over the Atlantic because there was a mechanical problem with the Pitot tubes. They didn't know how fast they were moving through the air. They thought they were moving. They were moving too slowly. So they actually had a structural failure in the airplane because they kept trying to dive and increase speed. Yeah.
So the cockpit, like the numbers will go to the cockpit, right?
They go to instruments, and the instruments. You can imagine nowadays it's all digital and all instrumentation. Yeah, but this will get converted by circuitry into an actual air velocity. So the guy in the cockpit is going to be reading the device is reading both total pressure and static pressure, but the electronics is going to convert that into the velocity of the plane moving through the air, right? So we use this also to measure the velocity of the air going through here and to measure the static pressure as well. Static pressure is what drives everything. Static pressure is going to be important because, as I'll discuss next week, when you design these systems, you figure out how much air you need to pull at that end. In order to pull that much air at that end, you need a certain amount of static pressure here to overcome the losses in the ductwork and the elbows and the turns and the hoods and so on and so forth. So the way you design the motors, the fans, and everything else is by learning how much energy the static pressure has to supply to give you the velocity of air that you need. We're not going to really get into the math of this whole thing. We do it when you take industrial ventilation. You do get into the math of the calculation of all this stuff, but it's really, really interesting stuff. And it kind of ties in as we move forward. It ties into how we make measurements in indoor air quality as well. So we're going to go over a bit of this next week, and then we're going to start moving into indoor air quality. And if you don't have an air conditioning system works now, I guarantee you by the end of the session next week, you'll know how to fix your own window unit. Okay? Well, maybe not, but you don't have the tools for it anyway, but you at least know how it works. Okay? Okay, guys, good night.